So the early universe begins as a big. The current model is the hot Big Bang. And this was, again, a modification of the hot Big Bang proposed by George Gamow. And so this is what we're going to be going through. The Primordial Era. That's the first few million years of the universe, before you had stars, before you had anything else, before you had galaxies. So the universe starts as a singularity. Everything in the universe, everything, space itself, starts as a singularity and expanded. It's not expanding into anything. Space is expanding. There's nothing outside the universe. You can't talk about outside the universe, because outside is a spatial term. The universe is all of space. Space is expanding. The universe is expanding. It was all a singularity. All of space is expanding. If you're anywhere in the universe, you see the same thing. All of space expanding from you. And you can only see as far back as the age of the universe. And so that defines the universe. There is nothing to expanding into. I mean, and the other thing that happens is time begins when the universe begins. Therefore, there is no before the universe. There is no before time, because time before is a temporal term. You can't really talk about outside the universe or before the universe. Though there are plenty of books that are out there, even a couple things written by cosmologists, like Before the Big Bang. That's nonsense, really. Those are books written from laymen, using terms the laymen would understand, but technically there is no before the Big Bang, there is no outside the universe. All of the universe, all of space, and all of time started as a singularity. Physics is limited. The shortest time that we can possibly measure is about 1.4 times 10 to the minus 43 seconds. This is what's called the Planck Time. The physical meaning of the Planck Time is a little beyond the level of the class. But we're gonna not worry about that. But anything that happens in less time than that, as far as we're concerned, pretty much happens simultaneously. We cannot describe what happens in shorter times than that, which also defines the shortest size. So the universe, as it's expanding for the first 1.4 times 10 to the minus 43 seconds, we can't really say what happens. We can start explaining stuff after that. In explaining the universe, we have to explain how forces work in the universe. Physicists recognize 4 forces. Gravity. We're all familiar with gravity. The electromagnetic force. In physics, we realize the electric force and magnetic force are 2 aspects of the same force. And so it's the electromagnetic force. They both relate to charged particles. At very small distances, there's 2 other forces, the weak force and the strong force. The strong force is obviously the stronger one, the weak force is the weaker one. Again, the way we just name these things. And when I was a student, we called them the weak nuclear force and the strong nuclear force, because the farthest distance they can interact is, like a fraction the size of the nucleus of an atom. The strong force, in fact, is part of what holds the nucleus of an atom together. The weak force is part of what holds neutrons together. Okay. Between the strong force and the electromagnetic force, there's only a factor of 137, about a similar factor between the electromagnetic force and the weak force. An enormous difference between the weak force and the gravitational force. A massive difference right there. And so the gravity is by far the weakest of all the forces. It's completely overwhelmed by every other force. Well, the reason it doesn't seem overwhelmed is that, unlike other forces, the electromagnetic force, for example, you have plus and minus. Like charges repel, unlike charges attract. So it can be both ways. The strong force, the weak force, they're very, very short range forces. They also have bidirectional stuff, but they're very, very short range forces, so they don't interact over a large distance. Electromagnetically, there's the same number of positive and negative charges out there, so they balance out. Gravity, on the other hand, is unique in its one directional. There is no anti-gravity. Antimatter does not have negative mass. It does not have negative gravity. So there is no anti-gravity. This throws a giant monkey wrench into a ton of science fiction stories. But there is no anti-gravity. Okay. We discovered that electromagnetic force is mediated by photons. Light particles, for example, going back and forth between things, that carries the electromagnetic force. Strong force is mediated by things that we call gluons. So this is part of what holds the nucleus of an atom together. It's part of what holds protons together. And so the gluons hold everything together. Gauge bosons are these short-range particles that mediate the weak force. So, and these things, we've all verified that these things exist. Since forces are all carried by particles that go back and forth, it is suggested, therefore, that gravity must have particles. And we've never found them, but we've already named them. We call them gravitons. Photons have no mass. Now, the gauge bosons and gluons have mass. They're temporary particles. They can't go very far because they're limited because they have mass. They can't go very fast. Gravitons and photons have no mass, so they both must travel at the speed of light. In fact, it does appear that gravitational waves do travel at the speed of light. So this is the forces. Interestingly enough, 1970s, it was shown that if you have enough energy, particularly enough energy density, the electromagnetic force and the weak force become indistinguishable. They basically unify into something called the electroweak force. So we've simulated that. We've done that in high energy physics machines. The so-called atom smashers, that they really don't smash atoms, but they're particle accelerators. This was also what was happening shortly after the Big Bang. The entire universe was in that sort of configuration, and so the forces were unified. In fact, when high energy physicists are trying to explain to laymen what they're trying to do, they sort of incorrectly say they're trying to simulate the Big Bang. And for people who don't know what they're doing, they don't know what the Big Bang is, and so that explanation just scares them. So it's not really a good explanation as to what they're doing. For your book, there's a graphic that looks like this, and it shows that at a certain energy density, and we talk about this as terms of temperature. So we'd say the universe at a certain temperature would have a certain energy density that makes the electromagnetic force and the weak force come together to make the electroweak force. You can also show that if you have enough energy and high enough density, then the strong force merges with the electroweak force to become something we call the grand unified force. And that happened when the universe was a little bit over 10 to the minus 35 seconds old. The universe was at that point. After that, then the forces separated. After the universe was about 10 to the minus 12 seconds old, then the electromagnetic and the weak force separated. At 10 to the minus 43 seconds, gravity started separating. Well, the thing is, we cannot explain what happens in this period of time. So gravity separated from the other forces during this period of time that we can't even explain. And so maybe that's why gravity is so wildly different from the other forces. The laws of physics seem to operate differently at that time. So the electroweak theory is the mathematical description of what would happen if you have the electromagnetic force and the weak force put together. We have the grand unified theory explains when the strong force mixes with the electroweak force to make one force. So then we have the universe has two forces, the grand unified force and gravity. So what they're working on, and this has not yet been accomplished, is calculate what the universe would be like if gravity were mixed together and you just have one force. That's sometimes called the super grand unified theory, or sometimes the theory of everything. And that would be what the universe would be like, and would describe how all these forces fit together. The forces also, again, we have, again, the gluons, they hold the quarks together. Photons carry electromagnetic force between charged particles. These gauge bosons or intermediate vector bosons, they work between quarks, electrons, and neutrinos. That mediates the weak force. It kind of what holds certain things together, like neutrons. So radioactive decay is involved with the weak force. Gravitational force, that holds all matter together. Okay. And so, and again, there, your book goes on to talk about the different kinds of quarks, and the various bosons that hold that mediate things together, and so forth. Okay, and then leptons, the weak force acts on leptons, and so the different kinds of leptons that are out there. And so Higgs boson is essential for describing how gravity works. Okay, now we don't have time to go into all the details of that. I wish that we did, but we don't. Physicists have attempted to try to explain how all this works. One rather interesting way of doing it is something called string theory. String theory actually, though, suggests that every point in space, rather than having x, y, z, 3 dimensions, every point in space is actually described by 10 dimensions of space and 1 dimension of time. So that would indicate that the universe is really 11-dimensional, not the 4 dimensions, not the 3 dimensions plus time, or 4-dimensional space-time that we're familiar with. And so that's a little bit more complicated. And that's, again, beyond the level of the class, but it does try to indicate that every spot in space can be described by extra numbers, extra dimensions. And so that does indicate the universe is somewhat more complicated than it currently is, than we currently think about it and see it. Okay, so as the universe expands, the energy density decreases, the temperature falls, the particle densities drop, different things start happening, and the character of the universe changes. It changes in part because these forces separate. Now, the forces separating is an interesting idea, and we'll talk about that in just a little bit. So what we'll do is I'll pause this video for now, and then we'll start with the next one here, talking about the Planck era, the first 10 to the minus 43 seconds of the universe.